Hey folks, in this video we're going to be talking about percent yield and prepare your hearts for some real life despair. I want you to be able to explain what percent yield is, or rather define it. And I want you to be able to calculate percent yield from experimental data. And I want you to be able to explain why being a chemist is hard. Also, talking is hard. Anywho, percent yield. Percent yield measures how much product was actually collected during an experiment versus how much product could have been collected. So the percent yield is going to be equal to the actual yield, what you actually get, divided by the theoretical yield, what you thought you could get, times 100. And so the actual yield is going to be what you actually get during a lab experiment, or really anything. This is going to be also called the experimental yield, but I use the word actual yield because it's easier. The theoretical yield is what you thought you could make based on calculations. And those are going to be stoichiometry calculations. So let's maybe look at an example in a second. But what you should know is your actual yield should always be smaller than the theoretical yield. If your actual yield came out larger than the theoretical yield, that means that something got weird. You shouldn't be able to create more than the theoretical yield. If the percent yield does come out to greater than 100%, it generally indicates that an error has occurred. Let's look at a fun example for starters. You bake a recipe that says it'll make 100 cookies. You only end up getting out 88 cookies. This is then your actual yield of 88 cookies. That's what you got. But you thought you could make 100 cookies. That's your theoretical yield. So your percent yield would be 80 divided by 100 cookies. 88 cookies divided by 100 cookies, then times 100, or 88%. So maybe this wasn't such a fun reaction because we thought we were going to get more cookies than we did. We were 12 cookies short of what we thought we would get. We didn't get all the cookies promised. But this is kind of the standard for chemistry. Pretty much no reactions give a 100% yield. If you have over a 90% yield when you're doing chemistry, life is going pretty good. So, as I said, we're going to mostly use these percent yields in chemistry. And so the first thing we need to do is calculate a theoretical yield. We're going to do that with stoichiometry, and we're going to need to know if there's a limiting reactant for this. And so then based on the limiting reactant, we can calculate an amount of product, typically grams or liters, that we expect to form during a reaction. And so we're going to determine our actual yield by performing an experiment. This is why it's also called the experimental yield, because this data comes from doing an experiment. And thus, the heartbreak of chemistry comes where, as I said, no reactions will go to total completion. So 100% yield is theoretically impossible. If you have one, it's probably because you goobered up. And some reactions are great if you get like a 20% yield. Those are really sad reactions. Some have even less than a 10% yield at best. So the percent yield is sometimes used as a measurement of how good a reaction is. If you're getting a high percent yield with a reaction, that's great. Yeah, and so something else that's going to affect our percent yield that's not necessarily just a reaction is how many times you do transfers between chemicals. Like every time you pour your chemicals into a new container, you're going to lose some of those chemicals. They're going to be left behind in the container you poured out of. Chemists will try to minimize these losses, but you're always going to lose a little bit of stuff like that. If you want to test this at home, like get some orange juice and then just start pouring it from one container into another container into another container, and you'll see that you're always going to have a little bit of orange juice left behind in the container you just emptied. Cool. So that's the thing that haunts chemists. But yeah, we do say if a reaction is good, it should have a high percent yield. Cool. So what causes these percent yields to suck? As I said, we could lose product when we're moving things between containers, or also if we're trying to purify products, we might lose some of our good stuff when we're taking out impurities. And other things that could affect our percent yield would be things called side reactions. Usually when we write a chemical equation, we only show one product or maybe two being formed. But in reality, sometimes you can form a whole bunch of different products. There can be many or a few ways a reaction goes, a few pathways, if you will. And generally, when you're doing chemistry, you only want the products formed by one pathway. So if there are other pathways, those will be wasting some of your reactants, making stuff that you don't necessarily want. Neat. Well, let's talk about how we actually calculate some percent, or we talked about how to calculate it. Let's just do some practice. So you calculate your theoretical yield for an experiment is 55.4 grams, and you only get 49.3 grams. What is the percent yield? Pause the video and think about it. Cool. Well, we have our actual yield. This is the stuff that is recovered. That's what we get. And we know our theoretical yield is 55.4. So we'll do the small number divided by the large number times 100. And in general, this is how things are going to go down with percent yields. Unless you've made a mistake, your theoretical yield, again, should be larger than your actual yield. So our percent yield is equal to this dude over, and we got an 89% yield. Fun stuff. Let's look at a slightly spicier problem. So here we've got a actual equation, and yeah, we're gonna need a reaction equation for that guy, I think. Yep, yeah, let's look at that. So we got 12.3 moles of iron, and they're reacting with all the oxygen we could possibly want. So we're not worried about limiting reactants, and we know how much iron we collect out of this equation. So first we're gonna need to, well, why don't you pause the video and we'll talk about it together. Try it out. Great, you tried it, let's talk about it together. First thing I'm gonna wanna do is figure out my theoretical yield. So I'm gonna use my moles of iron, and I'm going to do some sweet stoichiometry and convert from moles of iron into grams of iron oxide. So I can compare it to these grams of iron oxide, my actual yield. Cool, so my theoretical yield, I need to calculate. We'll do some maths, I'll do my conversion. Great, let's look at that. So yeah, we'll use some two conversion factors and we'll convert into grams of the product we're interested in. So now that I have my theoretical yield, I can plug into this equation and I can say, all right, my actual of 516.8 divided by my theoretical of 982 times 100 gives me a 57.8% yield. Neat. Maybe we should look at one more example. Should we look at one more example? Let's look at some otters. Oh my God, look how cute. Look how pensive. Oh, these otters are such expressive creatures. This is one rejoicing. Oh, rejoicing otter. But wait, what are those? What are those bubbles? Those are otter farts, just so you know. Anyway, one more spicy problem. Let's look at this. We've got 100 grams of sodium hydroxide. It's reacting with an excess of ammonium phosphate, and we're given a yield in liters of NH3, ammonia gas. So what is our percent yield for this reaction going to be? Well, here's our fun chemical equation. Why don't you give this dude a crack on your own, and then we'll go through it together. Okay, cool beans. Well, what are we going to do? First thing we need to do is get our theoretical yield. So we'll convert from the thing we know about, 100 grams of reactant, and we'll convert it to the product we're interested in. So we'll do some stoichiometry and change my 100 grams of NaOH into liters of NH3 because my actual yield is given in liters. Okay, so to do that, I will need to do some math. I will change first my grams of sodium hydroxide to moles. I'll change moles of sodium hydroxide into moles of ammonia, and then I will change from moles of ammonia into liters of ammonia. Nice. Okay, so there's what our math will look like, and we can find those conversion factors, except for this guy, on our stoichiometry roadmap or in our balanced chemical equation. And so now that I have a yield on my ammonia, I can calculate my percent yield. So I'll do my actual yield, the smaller number, divided by my theoretical yield, the one I calculated, and boom, I can calculate that this is a 96.2% yield. That's pretty dope. That's a really nice yield. Anywho, that's the end of this video. I hope you understand why percent yields are calculated, why they can be useful for determining if you should do a reaction or pick a different reaction, and I hope you also understand how to calculate percent yields. Ta-ta, and have a great rest of your life.